Thanks so much, Prof, for the privilege. Just be checking the number of participants in class. Yes, it's more or less the 10 minutes cannot do them because we started very early here in Nigeria, and many of our participants might not have taken their breakfast before joining the class. They need to do one or two things so that the energy will be restored and refreshing so that they can participate actively and concentrate well in the second leg of this session. Presently now we have 22 members on board. And well, around 14, 48, 49, 47 during the class proper. But why still giving them 3 minutes to join? May I quickly pass the information across again? We be ending this morning section by 12 o'clock. By 12 o'clock, that implies that you are having just an hour 30 minutes. Just an hour 30 minutes. And I believe many of our participants, they might have written their questions somewhere. They want to have ask questions and get them answered. By so doing, I believe we need not less than 20 or 25 minutes, if I'm not saying 30 minutes, for question and answer session. As such, I'm appealing to our teacher, Prof, to also look at his schedule so that when it is time, please kindly give us the privilege of answering question, asking questions so that you will answer them accordingly. One. Number two, our attendance form will be shared in this second leg of this morning session. Please, as I've pleaded earlier on, make sure you write your name the way you want it to appear on your certificate. Sir, ma, the attendance is compulsory. It's compulsory so that the program is not about I've made payment, I've registered. Yes, the goal here is not even the money, it's not even the registration. The goal is the knowledge, and the knowledge can only be obtained through this class. Please, your certificate will be issued if and only if you participated in the classes. And as such, make sure you register in all the sessions. This morning session, the afternoon session that will still come today, and the afternoon session of tomorrow. Thanks so much for your participation. Prof, we have 1 minute more. Thank you. We have seen your slide shared, but we are seeing 10:34. By 10:35, you can hit the ground, sir. And our population is increasing. We are 26 already. I think it's a good number to start with. Others will be joining us as we progress. Thanks so much, Prof. Yes, attendance sheet. Somebody just asked a question. Attendance sheet will be shared here, and you just key in. It's just like a Google form, and fill just within 10 seconds or 15, you should be able to fill it. It will be shared here on this platform in the chat box.
Okay. Good morning, everybody. We are welcome to another, after the short refreshment section, we are welcome back to the morning section of today's training. So we are going to move on with the supervised learning. So we are looking at machine learning concepts and frameworks. So looking at supervised learning. Again, remember the previous section, we discuss this. We discuss under the machine learning paradigms, the association rules, supervised, unsupervised, semi-supervised, reinforcement, deep learning, and like. So I said we are going to come back to this place because this is by far the very popular, most useful, and easier to build machine learning system with assured accuracy that is reliable and better. So better. So when we talk of supervised learning, so you can see it. Given the training examples, x1 and f of x1, that is, this is the output. This is the output. See, x1, f of x1. It means this x1 is the set of inputs for a particular sample. It could be, let's say we have features like weight of the patient, age, gender, family history. So this x1 could be x1, x2, x3, x4. No, this is a big letter X. It is a vector that has subsets. So all this weight is what we give here. And then the output, f of x. F of x for this, and the entire system, when I put the entire characteristic of this patient has a weight of 64, age is 72 years old, gender is male, and the history of the parent, he has no history of any disease of this sort. When you put it inside it, I'm saying that f of x1 is going to give me the output. Maybe this guy is diabetes, yes, or is not diabetes. So when you give this, we have another patient, another sample, until the last samples. This f of something is always giving all the output. Now, imagine we have, this is for some unknown function, y is equal to f of x. There's a function, y is equal to f of x. So we know for this, f of x1, we know it to be yes. F of x2, we know it to be no. So once you have, then we can be able to, what is this f that is relating x to y? We're looking for that f. So we want to find that f so that we'll be able to predict y is equal to f of x prime, where x prime is not in the training set. So this is the training set being provided. So during the training, I used to tell people like this to understand supervised learning. During training, we have y is equal to f of x. During training, we know x is known, y is also known, but f is unknown. That hypothesis function is not known. That is what we are looking for during training. We don't know this. We know input, we know the output. We know that this guy, we know the characteristic of this guy, this patient, but we also know the output that the doctor already confirmed that this patient is diabetes, this patient is not diabetes. But this f that is relating between x and y, we don't know them. during the training. So this is what we are looking for. So we want to find an f of x that can predict y prime, an output, is equal to f of x prime, where x is not in the training set. That if we know f after the training, so after the training, we are going to get this unknown out, f. Now we know f. Now we want to solve this. Y prime is not within the training set. It's different now. The one we are hiding before is equal to f. Remember, we already know the f. The f is hypothesis function h160 now. That h160, we will now put the value of x that we know. We always know, even x prime. It's not part of the training set, but we know it. You have a new patient. You know the characteristics of the patient. You took the weight. You took the age. You also know the gender. You also know the history of the parent. Put those information here. We already have this hypothesis function after the training. We don't know why. It will be able to tell you that based on the hypothesis function we have, this patient is either diabetes or not diabetes. This is the summary of the idea of supervised learning. See? So supervised learning is used for prediction of future cases. It's also used for knowledge extraction. That's why we can use it to run diagnostic analytics. Why is something like this in the company? What could be responsible for this in our farm? It will try to identify features that are responsible. Why is this guy diabetes and this guy is not diabetes? We try to track out what are the characteristics that are very important in determining if someone is diabetes or not. Now, let's look at the simple illustrative supervised learning problem. Here you want to decide to wait for a table at a restaurant based on the following attributes. Let's say you want to go out with your family to have dinner or whatever out with your friends. Now you go to the restaurant. These are the characteristics. You want to build a supervised learning machine, a machine learning model that can advise you whether to wait at a restaurant for a table. You go there, the table is full. Should you wait or should you go to another restaurant after the other restaurant? So there are some characteristics that may affect your decision. We model them. So that once you just pick up your application, you just put them there, you run it, it will ask you some questions. Better to go to another station. Oh, you wait. How do you build such? The first characteristic there is alternates. Is there alternative restaurant nearby? That is a condition. If you have trekked to the restaurant you are, if you trek there, or maybe you call a taxi that took you there, you may think twice if you have to call another taxi to come and take you to another place. So if it's far away, is there any alternative restaurant nearby? Or you have to drive another 20 kilometers? That is one question. Waiting area. Is there a waiting area for you? Is there a comfortable area you can wait while the table is being prepared or while until there is empty table? Is it Friday or Saturday? Is it Friday or Saturday? Maybe Saturday there used to be a lot of crowd, or Friday. Are you hungry? If you are hungry, these are some of the characteristics. So when you want to build a machine learning model, you need to think of what are the characteristics that can dictate what will happen in my farm. You bring out those data, you keep noting them down. Patrons. How many people are waiting in the restaurant? None. Some people. Full. The restaurant is full. Maybe you should wait for it. You wait. Nobody's there. So you can easily wait. Where are you going? It depends. Price. What is the price? Is it $1 dollar or 2 or 3 dollar? Is it raining outside? If it is raining or not? If it's raining, maybe you may not want to bring your family to the rain. You may have to wait. Provided you have a waiting area. Reservation. Have you made reservation before? Imagine you made a reservation, you even paid for it. Then, in that case, your money is stuck. You may not be able to go. Is it possible for somebody to have reservation and still leave? We will see. Kind of restaurant. Which kind of food? Is it pounded yam? Is it French food? Italian? Is it burger? Maybe something you so much like or you don't like. What is the estimated waiting time? Is it 0 to 10 minutes waiting, 10 to 30 minutes waiting, 30 to 60 minutes waiting, or greater than 1 hour? All these characteristics, we call them features. These are the features that will aid your decision. We want to use it to model, to build a model that can then advise you in future. The target decision is either we should wait or you don't wait. Yes or no. These are 11 variables. Now let's look at the data set collected based on these samples. Based on the feature I showed to you before, this data set were collected. This is the first participant. We call them sample. We call them sample 1. You can see the X1 I said before. It's a big letter, it's a vector. It has other small x1, x2, x3, x4, up to x10 here. This is the target, which is the Y. This is the Y we are looking for. This is the Y we are looking for. Now, so when you can see the first data sample we had, there was alternative. There was alternative restaurant near. True. There's a waiting area. False. There's no waiting area. False. There is a Friday. False. It's not Friday. It is Saturday. Hungry? Are you hungry? No. Yes. True. It's hungry. How many patrons are waiting? How many customers are waiting? Some customers. Not empty. Not full. What's the price of the food there? Wow. 3-digit dollar. Meaning that minimum of $100. Is it raining outside? No, it's not raining. Is there any reservation? True. There's reservation. Type of food, French food. How many estimated meaning? 0 to 10 minutes waiting time. What's the decision? This customer waited. He decided to wait. We now try to understand. As human beings, we try to understand why did he wait? Maybe because the waiting time is small. See? You will see another guy here, the waiting time is also small, but he didn't wait. Look at it. He didn't wait. He left. So it's not the condition. It's not one feature that is determining the condition. Maybe he liked French food. Maybe. But there's another French food guy here who also left. So you see, one single feature may not be able to tell you what is going to happen. This is where machine learning comes in. As human beings, we can analyze 1 feature, 2 feature. The moment the feature are becoming more, then trouble will set in. We may lose count of it. Let's look at another sample before we move on. There's alternative restaurants. There's no waiting area. Even though there's no waiting area, this guy still waited. Even though there's no waiting area, he decided to hang around. So what is making him to take that decision? So in this case also, no waiting area. It's not a Friday. He's actually hungry. But it's full. The place is full. Maybe because of it's not full here. It's a very cheap food. $1 single-digit price. It's not raining outside also. Reservation. This guy has no reservation. It's a Thai food. The waiting time is 30 to 60. What was the decision? This guy decided not to wait. He left. Can you see? See? Even though the money is cheap, he still left. Though it is full. But you have also here, it is full. Someone also waited, even though it is full, or it was full. So that's why one attribute may not be able to determine what will happen. So when you have this kind of situation, machine learning is very adept at modeling this. It will study these things and come out with an hypothesis function H is try to understand what is the relationship between these attributes, these 10 attributes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the output, the Y, that is making this guy to stay. This one is not staying. This one is staying. This one is staying, not staying. So what do? We divide our data into two. Divide the data into training set and testing set, training set. During the training set, as you supply the input, you give the output. You supply the input, it gives the output. The system will keep learning. It will be changing from H1. Maybe H1 is able to recognize the first one. Once you put the new second sample, H1 may not work. Maybe H7 will work this time. You keep adding one sample and the output. That is called supervise. You are supervising the training. Hey, please look at the output of this one. Try to come up. What's the relationship that is making this guy to wait and this one not to wait? After finishing with the training set, let's say we use 70% of the training, of the data for training, let's say here. The more the better. Let's say this is just an abridged form of the data. Maybe the data is like 1,000 samples. You just put this one here to fit the screen. So use 700 of the samples, 70% for training. Once you are done with the training, you are going to generate an hypothesis function, maybe H125. Maybe this is because we need a single hypothesis that can understand the entire data you've supplied. 700 samples, only one hypothesis function is needed. We now take this H125, and now you bring the testing set. Let's say this testing set number 1. You take this testing set number 1, you give it to this hypothesis function. Tell me, is this guy going to wait or is not going to wait? He decided to say he should not wait. The second one again, don't wait. Another one, don't wait. The fourth one, you should wait. So he got everything right because here, don't wait, don't wait, don't wait, wait. He got the 4. We put it side by side. We hide this away from it. We now compare the output with this. And they're the same. Sometimes he made mistake here. True, false, false, true. He got 3 right and made a mistake. That's fine. That accuracy will be 3 out of 4 times 100. This is how the supervised learning takes place. So the supervised learning, as I've explained, you have this unknown function. We are looking for a good approximation of f, where x will provide some representation as it may be. So the process of mapping a domain element into representation is called feature extraction. You have to extract the right feature. See, here is about people waiting in a restaurant. When you want to work in your chemistry lab, it has to be something related to what you are doing. What are the questions that can contribute to taking the right decision as your output? In your farm, you have to ask questions. You have to come up with features that are related to what you are modeling. I want to predict if a student will drop out from school. We're asking him, what does he eat in the morning? Is it pounded yam or rice? How does that determine if he's going to drop out from the university? So we have to ask appropriate questions. That is why feature extraction matters. You have to extract the right features. Our X, which is the feature, may be 0, 1, maybe numbers, yes or no. You're asking people, have you ever visited the clinic before? No or yes. Any of your family member had this disease before? No or yes. Sometimes A could be real number, 25.5. And sometimes it could be categorical data, like gender. You may have gender, which is going to be male or female. Then the target function, which is the label, the output, can be any of these 3. F of x, which is the output, could be -1 or +1. We call this binary classification problem, which is yes or no. It could be multi-class classification problem, 1, 2, 3. Let's say you want to know your grade in exam. Is it A, B, C, D, E, or F? That's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1 start for A, 2 for B. This is called multi-class classification. These 2 are under classification. And then your X may be a regression. That is, X is containing a real number. Real number, 20.5 is 0.23. Whatever you can call real number. That is under regression. That is supervised learning. We talked about how it works. Then we talk about the inputs you need to them, and also the target output you are actually dealing with. So we said under the type of supervised learning, we said we have classification and regression. The output for classification is containing 1 up to C, where C is a constant. If C is equal to 2, we have binary classification problem. That is 1 and 2, yes or no. It will rain or it will not rain. But sometimes we have multiple classes, like a stock market is 3. It could be 3. It could be 2. Will the stock market go up or go down? I may create a third one. Will you go up, go down, or be stable? What we have today will be the same thing as that of yesterday. It means it has 3 classes. Now, sometimes it will be more than 3, like student result. A1, B1, B2, C3, C4 as the number of options you have. In regression, it is a real number. For example, if I want to predict whether a patient will die from a disease within 6 months, that is classification. Pay attention to this. I want to predict whether a patient will die from a disease within 6 months. This is classification. Because I mentioned 6 months does not make it to be regression. I've seen students who made these mistakes. Because there's 6 here, it must be regression. No. How do you determine what is asking? I want to predict whether, whenever you use whether or not, we follow. So it's yes or no. How you know if a problem is classification or regression is, can I formulate it as yes or no? If you can make it as yes or no, it is a classification problem. If I want to predict how long the patient will live, that is regression. This patient will live for like 6 months and a half, 3 years and a half, 3.5 years, 4.5 years, 17 days. This is regression. So we have to get it very concisely right. And if I move further there, okay, I gave further example. This is classification. We predict categorical values. It's like more partitioning things to 2 or 3 places or more. Should I give him loan or not? We want to build a loan application process modeling for a bank, for a Jais bank, if you should give a loan to a particular person or not. Is this spam email or not? But for regression, we want to predict continuous value, like stock markets. The stock market, what will be the value of the stock market? 20 naira 0.5 or what? Credit score. What's your credit score? Temperature. What is the temperature outside? This cannot be yes or no. We need number. Rating in any system. So that's why you see here, you're going to predict actual value, 0.2 or 0.4 or in between. While classification is more about partition. Let's look at these activities. For example, of classification and regression, we want to diagnose diseases. The feature will need property of the patient, symptoms, or lab tests. You can get lab tests, or you may ask some questions verbally, questionnaire based. The output is disease. You want to predict he has a disease, or you want to recommend the therapy you should go for. Part of speech tagging, an English sentence, the can will rust. The part of speech of a word in the sentence can be predicted. I want to predict what is going to be the part of speech of can or rust in this sentence. Face recognition, we have bitmap pictures of people's face. You want to name the person or a property or identify who is that person is. Then we have the automatic scanning. You have input, bitmap picture of road surface in front of the car. What's the degree to turn the steering to? This is regression. Should I turn left or right? That is classification. You can have a problem that you can formulate into more than one modeling scenario. I have a automatic driving car. I want to decide, should I go left or right? That is first decision to be taken. That one is classification. The next is to determine, if I'm going left, what is the degree that I should turn my steering? By 40 degree or 50 degree or 360 degree or 180. Want to go back. So that is, it means you can have a problem that can be formulated as a regression, at the same time also a classification. The first, we call it multi-stage predictive solution. Multi-stage predictive solution. So your client comes to you, you have a problem, okay, first of all, predict, should I go left or right? Hey guy, you are going left. Okay, if I'm going left, how should I turn my steering? By what degree? The degree of turning may be 36, 45 degree, depending on where they want you to drive to. And sometimes you solve this multiple, especially in autonomous car, autonomous vehicle, you solve this predictive continuously. Should I press my brake to slow down or not? That is a classification problem. Slow down or not? Should I run faster now, or I should still maintain my normal speed? Yes or no? So you have thousands or even millions of modeling system that is going on when you say you have autonomously driven vehicle. Now, again, understanding classification versus regression. You get ready for your own assignment now. I mean, in your interactive answers. I want us to, you have to give me example of classification and regression in your own area of interest. If I want to predict whether a patient will die from a disease within 6 months, I say this is classification. If I want to predict how long the patient will live, I call it regression. Now, participant, you should come up with examples in each category. I want to see you. Please, let's chat. What is your own example, your own area of interest? Give me one example of classification and give me one example of regression in your area of interest or your area of specialization. Now I'm going to be checking. I want to see the first to provide example. Example of classification. Classification is anything you can formulate as yes or no in your predictive solution in your area of interest. And regression is if it involves predicting numbers, actual values. I hope you are getting my analysis. I'm yet to get any response. Let me assume we have, okay, good one. The first one came in. Classification predict whether a patient will have epilepsy or not. Excellent. That's a good one. Will it rain tomorrow or not? That is classification. Student will pass my course. Classification. How many students will pass the course? Excellent. That is regression. Good. Good. We are getting the understanding. For classification, can TiO2 remove PB in wastewater or not? Excellent. Can TiO2, that can the titanium oxide, can it remove lead in wastewater? That's a good one. That's classification. Is the coastal area considered vulnerable? That is classification. Excellent. Yes or no? So if it's vulnerable, then we want to see what can we do to protect people there, to prevent disaster. Will there be fire? Classification. How many acres of fire will burn? Regression. Excellent. Thank you. Thank you. Keep it coming. Yeah, keep it coming. I want more. So that's a good demonstration that we are getting it. Will there be a bumper harvest this season or not? Classification. Excellent. Now, what of the regression aspect? We got bacteria cause metabolic syndrome. This is classification. Which diet will contribute good gut bacteria? Regression. Which diet? Which diet? Which diet is a category? You may not be able to model which diet as a regression. You see, you can categorize the diet into category. We have like 15 diets. That is a multi-classification problem. diet 1, diet 2, diet 3, diet 4. You want to predict which of them will contribute to good gods. That is a classification problem, although there are many diets, because predicting number does not arise in this example given. I hope that is clear. So which gut bacteria will cause metabolic syndrome is a classification. I agree. But which diet will contribute good gut is also a classification problem, because that is categorizing diet into groups. It doesn't involve number. For you to say something is regression, it must involve number, real number prediction. 20, 25.3. I want to predict the age. I hope that clarifies. Regression, what is the concentration of lead remover at different reaction time? Excellent. That's another application into the treatment, water treatment. That's a good one. That is regression, because number is involved. When will a patient have epileptic attack and frequency? That is another one. You want to know the day and the time. Is it the third day of the week? That could actually be a classification. And the time will become the regression. The time becomes the regression aspect, because your number is now involved. But the day of the week can be modeled as a classification. You see, Sunday is 1, while Tuesday is 2, and the likes. Thank you all for the coming. Will this particular product be bought or not? That is classification. Excellent. What will the harvest look like this season? What will the market look like this season? This is not direct. It's a little bit, we call it, it can be translated to be regression or classification. What will it be? Is it going to be good or bad? That is regression. That is classification, sorry. Will the harvest look good or look bad? That is classification. What will be the amount of harvest? Then when you're talking of amount, you're talking of maybe production in tons, 20.5 kilograms of tons of maize, then we are going regression. Regression must have number involved. I hope we are taking care of that. We are taking note of the correction. So classification, will there be flooding this year in Lagos State? That is excellent. Classification, yes or no. Regression, what level of flood and how many times? Excellent. That is regression. What is the level of flood that you are going to have? Are you going to, do you measure flood by number? So people in that area, if you measure it by number, that will be regression. But if you don't measure it by number, it may be a classification problem. For example, I want to know the level of flood in Lagos this year. Is it going to be huge, minimal, or really disastrous? That could be it's a classification problem. Minor, medium, and disastrous flood. That is 3-class problem. It's a classification. So we have to pay attention to how we formulate our regression or classification problem. I think we've gotten more than enough. Thank you very much all for coming. How many products will be sold in a week? Regression. Excellent. Number is involved. Will I get my money back? Classification. Yeah. How long will I sleep? That is regression. It could be 20 minutes, something, or 1 hour, 30 minutes. Number is involved. So thank you. How long does it take a coil wall to start decaying? Regression. That is it. Yeah. How long? Number is involved. At what dose will diet be contribute to gut bacteria ameliorate? At what dose? Okay, that's a good one. Maybe 2.3 kilogram of dose or 2.3 milligram. That is fine. That is a regression. Thank you very much. What is the price of stock tomorrow? That is regression. Will I make more sales this coming month? That is classification. What will affect more sales this coming month? What will affect it? That could be classified into classification and regression. It depends. What is going to affect? It depends. So can you formulate it into categories? Rain will affect it. Resumption of students to school will affect it. That could be a classification problem. So before we can call something regression, it must have number. Let's all pay attention to it. Number prediction must be involved. How long will an organization be in existence before it pack up? That is regression. Thank you very much, all. That's a good one. I want to predict whether we go to work tomorrow. That is classification. That's a good one. So what will happen? Yeah, thank you all for the wonderful responses. It shows I always like interactive section so that everybody is involved. Classification, will my student be able to use ML effectively after training? Yes or no? That's good for me. I need to deploy a model to know who among you will use it successfully so that we can work closely with those people identified as not able to use it. Excellent. Regression, how many of my students will make money using ML as an entrepreneurial venture? That's a good one. Regression. Thank you all for the wonderful responses that we've gotten so far. Now let's move on. So now that you have been able to identify what you can use it for in your own area of interest, so it's a good one. Yeah, thank you. Now, so in supervised learning approach, it has approaches. It's a category of supervised learning. We have classification, discrete prediction, regression, continuous prediction. Common consideration, you need the feature. You need to know the feature. Sometimes we do feature selection. Your feature may be too much. That will cause problem for you. We talk about that later. We call the cost of dimensionality. The more the features, the more the number of samples you need. But samples are always fixed sometimes. So if your number of features is too much, you may have to select the feature that is better. Not all features will give you good result. So if you have 2 features and you have only 30 samples, better than having 15 features and 30 samples. You may not be able to scale, but then bring it up and let's see what you can get. The functional form, what's going to be the hypothesis function? We go in the class, we call it classes, 2 classes, we call it multi-class. Regression, we call it regression variable. That's the output. Things to be predicted, or the definition of things. On the definition of things, which we'll call the instance to make prediction for, it can be individual. We want to predict something about you as an individual. Will you pass this exam or not? It could be about a family. Which family in the neighborhood will win? We win the best neighborhood of the year, neighborhood membership of the year. Which of the family in the neighborhood we get baby next, where we are going to go to celebrate childbirth? You know, that is about family. Neighborhood also, which neighborhood will be flooded in a particular state? Which neighborhood? So it means you need to look for characteristics that will describe neighborhood when you are building your data set. So the choice of the descriptor, the feature you need for neighborhood is not what you need for family. It's not what you need for individual. Application that centered on individual must have individual-centered features. And those for family will have family-centered features. For neighborhood, it will be neighborhood-centered, etc. It could be about state. I want to predict the state that will have the best developmental project. It could be a country. So we have to adjust our features appropriately. So in the formal descriptor, X is set as the instance. We give the training data, example D, which is gotten from X. The target function C map X to 0, 1, the output. Given a hypothesis function H, the hypothesis function, hypothesis space is H. Call it H. Inside that H, we have different possibilities. H1, H2, H3, up to Hn. That's no limit. So you keep trying different hypotheses as you add more samples. So we want to determine an hypothesis H in the space such that H of X is equal to C of X. So that the hypothesis function will produce the same output you already have for all X in D, for all the training sets. That is, the expectation is that when you train, your selected hypothesis function must be able to identify all the samples correctly, like the output given. See, this lets us to what we call the hypothesis space. The hypothesis space determines the functional form. Functional form. This is H. Every algorithm has a different hypothesis space. Inside the hypothesis space, you have H1, H2. This is for SVM, for example. K-nearest neighbor has another hypothesis function, KNN, H1, H2. And that's why the way it works here is different from the way this one will work. And that is why Ensemble has always demonstrated better results. We'll discuss that one later, because it uses different spaces to get decision made. So the hypothesis space defines what are label rules or functions for classification. Each classification method uses a different hypothesis space. Let's pay attention to that. And that will land us in what I call inductive learning hypothesis. We must take note of this. Is the working principle behind supervised learning. If the hypothesis works for enough data, it will work on new examples. That is why we always divide into training and testing. If the hypothesis works for enough data, it will work on new examples. In other words, any hypothesis that is found to approximate the target function well over a sufficiently large set of training examples will also approximate the target function over other unobserved examples. This is another way to say it. That if you have a training set, you train it well, and it's able to, because the idea is in the training, during the training, we're supervising it. As I'm giving the input, I'm giving the output. This is the output. This patient is diabetes. This patient is not diabetes. This patient is diabetes. It's understanding it. Once I train it, I'll give this code back to it again to tell me the output. It must be able to recognize what it has seen before. Maybe it's only making one mistake or the other in the training set. But the testing set must never be exposed to the training set, to the training post, during the training stage. It's to be kept outside the training phenomenon. We are now saying if the hypothesis you have selected, maybe H120 is the final hypothesis function you choose. If it works for enough data, that will be coming later. The question people ask me is, what amount of data is enough? I say that is the data. What is enough in one feed may not be enough in another feed. But generally, the more the data, the better. But whatever start with it and see what you get. Sometimes we frame it in such a way that we want to learn a mapping from X to F such that H of S given theta, theta they are the parameter of the algorithm you are using, or the hyperparameter. We want to make it to be close to Sorry, so that was a technical issue that took me off. Apologies. Yeah, like I was saying, here you have we can relax the rule. Instead of making the two to be equal, we are saying if they are close together, that is okay. Because sometimes you may not be able to have your model to understand the entire training set 100%. In fact, when you get 100% in your training set, it may be overfitting. You may start to be worried that maybe it has overfitted. So these are examples of rules. For example, the hypothesis function may be like W1, X1 plus X2 plus the weights that are added. Or it could be something like this: X1 or X2 and X3 or X or not X4. This will determine the output. This will be yes or no. Finally, 1 or 0. So this could be example of it. And sometimes it could be complicated regression line. So it depends on the problem we are solving. So when you use supervised learning, so you have that particular idea where this can go and where this one can come in. That will did happen with tomato. So you give the features, get the features for the F, so that you'll be able to know this is apple. Later, you can then deploy as the case may be. So this is the machine learning framework. You have the output, you have the predictive function and the imaging. This is the one I call model, or I call the hypothesis function. So I told you already during the training, we know this, we don't know this during training. But during testing, we know F already, we know X, we are looking for Y. And that is why machine learning can easily tell us, once you build the model, you can use your model for subsequent predictive solutions. Yeah, this is what we call the generalization rule. Generalization. See, when you have a training set, this is the training set, the training label. As we are giving this to the model, we are telling, okay, this is apple, this is tomato, and the likes. The testing set is never shown to it. So the generalization is how well does a learned model generalize from data it was trained on to new test set. We want to know how well does a model learn and generalize from where it was trained to the reality. That is, we always want the difference performance, the training set performance, and the testing set performance. We want it to be close. You don't want your training set to get like 100% accuracy, and when you now bring the new one, you're getting 30% performance. That's bad. We call that overfitting. It means your training process just memorize these guys. So we better have a system that got like a 96%, and then you're able to get like 93% here. Excellent. You see? So we want the gap between the training set and the testing set to be a little bit very small. In fact, in very rare cases, you may have testing set that is better than training set. In the entire application, in the entire practice of AI machine learning training, in my entire career, I've gotten it one time. We had a data set that was huge, 48,000 samples in Arabic numerals number recognition. We achieved, I think, 99% training and 100% testing. Very rare, but it happens once in a while. This is what we're always looking for. But at least the difference between the training set performance and the testing set performance should not be too wide. This is what we call generalization. How well does a learned model, the model you have trained, how does it generalize from the data you train it up to new test set that has never been seen before? So when you are getting 96% here and 91 here, or even 85 here, that's still fine. But when you are getting 90-something here, you are getting 20 or 40-something here, that is overfitting. It means your model is not able to generalize to unseen situation. So how do we check the generalization ability of a model? To check the generalization ability of a model, you estimate the generalization error. There are two ways of partitioning the data. Number one, we call it the holdout method. hold out method. In the hold out method, you divide your data into 2 or into 3, depending on the availability of your data. If your data is huge, is big, then you divide into 50% training, 25 for validation, and finally you bring the testing set to come and check. But if your data is not that very big, you can divide it into 2. 75% for training. All the process of training, hyperparameter optimization, you are going to use this 75%. This 25% will be kept outside for testing. You bring it later to come and test what you have built. Either you divide into 3 or you divide into 2, it's okay. The second option is the one we call n-fold CRUD validation. N-fold CRUD validation. This is when you have few data sets. Or sometimes we use it on the training set to do hyperparameter optimization. So we'll explain how the two works now. When you have the full data set divided into 2, training, usually people use 70% and 30%, or 75% for training and 25% for testing. It could be 80% for training and 20% for testing. These are just the range, it depends. Some people use 60%, but I see it very small. Your training needs to see more data set. But people also use 90%. Personally, I see that it's already getting too much. You are going to have only 10% for testing. That's getting really little. So 70 is common, 75% is common, 80 is common. But whatever you use, you need to document it in your report. Very important. You need to document it. Otherwise, you're publishing a work, you don't write it there, they will reject the paper right away. That is if it is not a junk paper. Because junk paper, they just want to collect your money. They don't read what you have done. But a good peer review paper, if you don't state how you divided your data, it means no one can reproduce your work. That paper stands rejected immediately. So once you divide into training and testing, then you can move on, as the case may be. Okay, I have been timed. Okay, we try to see. Complete a model using the data in the training set. This is, yeah. You see, you have your data, you divide into training and testing set. You can see, don't need the training, you don't use the testing set. So, and then you can check the prediction of your outcome. Sometimes if you have more data, you divide into 3: training, validation, and testing. The training and the validation set, they enter the development house, while the testing set is always kept outside. This is for final evaluation to see how your trained model is going to perform. Then, in the n-fold CRUD validation, here you partition the data into like, it can be 10-fold. 10-fold. If your data is sizable, it could be 5-fold. Your data is small. It means you divide the data into 3 or 4 or 10. You see, you use every other partition. This data are divided maybe to 5, for example. 1, 2, 3, 4, 5. If I have like 1,000 samples, it means this one will be 200, 200, 200. So I will use 800 to train and this one for testing. Next, this one become testing or validation. I'll use this one will become part of the training set. Next, I'll move it down. I'll keep moving it until every partition is used as a testing set or validation set. So if you divide it to 5, you're going to have second partition, 5th, until you have final one. This is an example. I have my data set, 1,000 samples, divided into 10 places. It's going to be 100 sample, 100 sample, up to this 100 sample, everything 100, 100. So I will use this as a testing set. All this one from here to here we use for training. Next, this one will become part of training, while this one will become testing. So I keep shifting everyone one by one. This is partition 1, partition 2, up to 10. This one is going to be used as the validation set. The result here is maybe 80%. This one is 86. This one is 75. I will add everything together, the total percentage, I find the average, divided by 10, then partition. If I partition into 5, then I'm going to find the average of the 5 results. This is the result of when I use this guy to test, when I use this guy to test, and when I use this guy to test. Add everything together, divide by the number of partitions you use. That is 10-fold cross validation. This is how we check the generalization ability of a system. So I believe that is clear. You have your training set, give it to you extract the image, you have the training label telling you this is apple, this is mango, this is this. You produce the learn model. During the testing stage, you have a new test image that has never been used in the training period. Extract the image features, bring the learn model here. And then it will tell you what is this guy here. That is how the training and testing work in a supervised learning. A generic supervised machine learning framework is shown for you here. There are like 3 minutes more. Okay. It's shown here. Start AI, I call it data preparation stage. I call it learning from data stage. And this is carrying out prediction and interpreting your result. So you have your preprocess the data. Don't do too much preprocessing. I told you, always let the data speak. Do the essential one. Model building, test your model. There's need to refine the model. Yes, do parameter optimization. Keep doing that iteration until you are good. Build the final model, validate it, predict using the model, analyze your result, and identify hotspots. What you need to do, future research directions can be identified at that point in time. So, yeah. So when you learn a class from a family, it's learning a class from examples. Let's say we have a class C of a family car. Prediction is we want to predict, is a car X a family car or not? Knowledge extraction. What do people expect from a family car? You want to predict positive or negative. The input represent price of the car and the engine. These are the input, the representation. You see, once you have the input, then you'll be able to predict, okay, is this car belong to family or it doesn't belong to family? And you can build a system like that. So this is an example of how hypothesis space work. You have the hypothesis space. You can have the false negative, the false positive. We'll come back to that later when we do the practical demonstration of the system. So we have H, the hypothesis space we have selected is contained in the hypothesis function contained in the hypothesis space between S and G, as the case may be. Okay. Yeah, I'm rounding up. Why this is the regression, this is where you predict actual numbers. You predict numbers. This is for classification, why this is numbers. If you are inside or you are outside, we know where you belong to. So we have different algorithms, we'll be discussing them later on. Then in the regression case, it's number. You want to predict actual values. So you have lines, say a straight line you want, or you allow a little bit of curve, as the case may be. So in the performance measure for regression modeling, so we have different quality measures you can use. The correlation coefficients, how close are you to the actual value I expected to have? We have the root mean square error. What is the total root mean square error, which is the formula for it? Your modeling application will give you the result directly. So we have other evaluation criteria like mean absolute error, mean square error, mean percentage error, coefficient of determination, and host of others, the case may be. In the classification realm, we have the classification, we have the accuracy. We want to know how many were correctly classified and how many are falsely classified. We'll definitely look into this when we move to the practical section. Definitely, that will be in the afternoon, God willing. We're going to demonstrate, look at few algorithms, how they are working, and also demonstrate by running experiment for us to see. This is an example of a classifier. We call it k-nearest neighbor. You see here, these are training example. This is class 1. This is class 2. Class 1, class 2. Now we have a new sample. We want to classify it. This sample now drop here. You can use k-nearest neighbor. We draw a line to join these guys. You see, we draw a line for it. So we want to label X based on the nearest neighbor. Who is nearest to this guy? This is the guy that is nearest to him. So we say this guy belongs to class 1. So this guy will be classified as belonging to class 1. That I'm using k is equal to 1. K is equal to 1 as an example. Sometimes I move k is equal to 3. It means in that case, all we need is a distance function for our input. No training is required for k nearest neighbor. We call this very simple algorithm. We are going to look into it in detail, like I said, in the afternoon section, God willing. So why sometimes we have linear classifiers that looks for linear separator that can separate these two samples. So when new samples are coming in, if you come here, then you belong to this side. If you come here, you belong to this side. These are linear classifiers that support vector machines and the likes, as we're going to see. Many machine learning algorithms to choose for. There are so many of them. We have support vector machine. We have neighbors, Bayesian network, there's discrete regression, random forest, XGBoost, k-nearest neighbor, neural networks, etc. However, the question that comes is, which of them is better? None of them is better. No one can really tell. So when someone tells you that, oh, the best algorithm is this, you know that it doesn't have better knowledge of machine learning. So support vector machine is a very powerful one. We have used it a lot. However, we have also used it in some application that it doesn't work. It doesn't perform. So no algorithm is inherently better. We have to check. It depends on the data you are having. And that's why I always say, let the data speak. Once you're using all this data to be able to know if it's appropriate for this. What to remember about machine learning model, there's no, we call something no free lunch. Machine learning algorithm, they are tools. They are not dogmas. Dogmas are a concept that doesn't change. Belief system. But algorithm is not like that. Some people jump to deep learning. Anytime they have problem to solve, they go to deep learning. And deep learning doesn't solve it for them. Because they think that deep learning is for everything. You have to know when it is appropriate to use a particular method. No classifier is inherently better than any other. You need to make assumptions. You need to make assumption to generalize. Try simple classifier first. Another principle of in machine learning, you have to know. Try simple classifier first before moving to more complicated one, so that you are not, you will not waste your time, so that you are not disappointed. Better to have smart features and simple classifiers than simple features and smart classifiers. That is, when your features are good, the data you are bringing up for your training, they are well collected, well curated. You are not bringing data that are not relevant to what you want to predict. Then a simple classifier may work wonder for you. It's better than having simple features and smart classifier. Even the smartest of classifiers may not be able to bring out the insight because your data is dirty. You've collected wrong features. So we have to pay attention to this take-home guide, as the case may be. Use increasingly powerful classifier with more training data. As more data is becoming available to you, then use more powerful classifiers as you move on. Always remember the principle of no free lunch. Here, to enter this place, you can eat there for free. But to enter, you need to pay $10 before you enter. But once you get things, you can eat for free. How many food you want to eat? Will you be able to finish even $10 food finally? That is why we say there's no free lunch. You have to think around it. Either you are paying the money back directly or indirectly. So this is it. So we have looked into classification and regression, where you predict discrete class and when you have number continuous value to be predicted, as the case may be. And the continuous classification may predict a continuous value in the form of probability for a class. When you use a classification algorithm, it will produce class A, 0.8, class B, 0.2. Probability is saying A is going to be the final selection because the probability is higher. Okay? For regression, may predict discrete value, but the discrete value in the form of integer quantity. It may predict your age is 25. Yes, exactly. That's okay. It's a regression problem. So we evaluate classification using accuracy, confusion matrix, and others, while regression is often evaluated by root mean square error. Very common to use root mean square error, correlation coefficient, and most of others. So thank you very much for listening. So I believe that's a good place to call for this section so that we can take question and answer. Thank you very much, coordinator. Over to you now. I believe we have it.
Thanks so much, Prof. Once again, you have really done justice to the work at hand, and we can't thank you less. We sincerely appreciate what you have done for us, and also to our very distinguished members and applicants. Okay, the excellent members now. We've gone beyond the level of application. Thank you for your cooperation and understanding. As I said, they are back, all of them, except like one or two. That might be because of internet that is fluctuating from the side. Everybody is back after our short break. I think this is wonderful and commendable. Yes, without wasting much of our time, we'll be taking our questions now, clarification, and if there's any comment, everything will be noted. You have the privilege of asking your question by raising your hand, and you will be called, or you want to put it in the chat box. It will also be picked there and read so that our professor will answer the question without wasting much of our time. But I just want us to go straight. Please go straight to the question, because we are to leave the platform by 12 o'clock or a few minutes after that, so that we can go and relax for 1 hour, 30 minutes or 2 hours. We'll come back for the class by 2:30 for the second session of the first day of track 1 2026 ASOM AI summer boot camp. Thank you. At the end of the session, 1 or 2 announcements will be made. Please, let's go ahead. Raise your hand, and when you are seen, you will be called, or you just directly put your question in the chat box.
Okay, thank you very much. So we are now in the question and answer section. Sorry, I can see somebody. See Mr. Sorry, Salahu Musli. Okay, Musli, Mr. Salahu Musli Ayafe. You have the floor. Ask your question. You can unmute yourself. Okay, I will allow you to unmute yourself. Now, unmute yourself now and ask your question, please.
Thank you very much, Professor.
You're
And
welcome.
also, I thank the moderator, Dr. Tajuddin. I'm very happy to be part of this, and where I actually get the information, the last time you came for our CONAC conference here at Fountain University, you actually opened our eyes. That is the reason some of us actually joined this call. So I want to thank you for that, and the privilege particularly granted to me to be part of this track 1. In the past, I had opportunity of anyway with little knowledge or none to deliver a talk on the AI in nutraceutica. AI in nutraceutica, that is the role of artificial intelligence in the functional food. So while searching through literature, most of the time we'll be talking about data. So my question now is, with this machine learning, so how are we getting our data, in this case, accurate data? Because in most cases, there are some saying that data in Africa is different from data in the Westerns. Also, like in the area of genetic configuration. Our genetic configuration with the Western is somehow different. Now, curating data, so, and interpreting those data in relation to our own, maybe we are our own now is now the testing data. We are now testing data with the data that is totally alien to us. How can we now consider or validate or rely on this type of data and the results? That is one of the things that is actually baffling, trigger my mind concerning this data of a thing and how to get exact data to work with. Thank you very much to give space for others.
Okay, thank you very much for that question. And thank you for the compliment. And I'm also happy that the Corners Conference gave the opportunity for you to know about this course. And we welcome you and wish you all the best as we explore together how we can do positive things using machine learning and AI.
Thank you, sir.
I've always say to people, the only thing necessary for evil to triumph is for the good ones to do nothing. There's so many powerful, positive things we can do for humanity using AI and machine learning. While some guys are busy developing the negative one, so the good ones need to think of, okay, how can we use it to improve our lives? So on the question, yes, data is a very wonderful raw material for machine learning development, its application. The good thing is that it's always very cheap. Data is wasting away. See, wasting away everywhere you go. Parastatus. Imagine just knowing the number of people visiting your ministry every day, your office. You can build a simple machine learning system that can tell you the number of people that will be coming next few weeks. So you can make preparation, even you can identify what are they likely to come and do. Which service? It has gotten to that level, people already using it. That will improve your service delivery. Imagine you have a shopping mall, 2 branches close together. Your system AI identified that this branch will be overloaded with customers this day. You can move some, and the other branch has been projected that it is going to have very low patronage. Move some people from there to this one, so that customer will not be complaining of too much waiting time. So there's so many things we can use it for. However, data is also available, but we are not curating it. We are not gathering it. We need to start it from schools, from parastatals. Let us start keeping our data. Government need to make policy. I know some governments of some countries, they made it the policy that every ministry, agency must have their data set online. And it's a machine order. You have to start employing data entry clerk. The data is there on the logbooks and those, even in the farm. There are so many things in your logbook in the farm, but it's not yet available for modeling. Let us mandate more job for data entry clerk people that will have to be employed. Later, you can train them to even become machine learning model builders, engineers, and also for that. However, by the time you are going to have the data, you start from what is available. Yes, the point you made is correct. When you train model for Africa, you can't use the same model for another place because the genetic makeup in their body is different. Yes, that's why when you use the data from a particular country to model, the same topic, you can model it using data from another place. It's still the valid research. Because research has identified that people carry different characteristics in their body depending on where they live. Is it a hot region? Is it a very cold region? So even if you move from one place to another, your body system starts changing. You'll be surprised. Your nature will change to accommodate where you just arrived at. So in that point, you may not be able to use data from other places to generalize to your own locality. However, as a starting point, you get data online. In the last presentation we made in money, we're going to upload all those things in the WhatsApp group. For those who are not yet subscribed to the WhatsApp group for this training for the summer camp, make sure you are there. All the recordings will be put there and also the materials. The list of data sets, sources of data set have been given. There are so many of them. Go online in your own area, you want to work, get data set, free one. Start using it. Test it. Where inwardly now, wow, this is how it works. You now start gathering your own data from those systems you are using. That is fine. But don't wait until you get your own data before you start doing something. So start from available data set online, where you now look at that, study the data. Oh, okay, this is the data. Start gathering your own data gradually until you are there. Even 15 samples is a good one to start. We've modeled data with just 16 samples with very unique and excellent result. This is a support vector machine, which has the capacity to actually capability to model in the presence of few samples. But the more you have, the better. So it is real, but we have to start from a place, start gathering the data. As you are gathering the data, be careful what you are gathering, because it's garbage in, garbage out. If your data is bad, it will affect your model. It's better to gather something very clean, and later you start complaining of that the data is not fine. So I hope I answered your question.
Thank you very much, Professor. Jazakumullah khairan.
You're welcome. Okay, it seems now we have questions in the, yeah. Okay, thanks, Commissar Leo Lawale Abdulrazak. Thanks so much for the wonderful session, Prof. What's the major difference between NLP and LLM, and where do they relate? So yeah, can you give an insight of a parameter to me? Okay, thank you. You see, like I said, machine learning is the big new guy in the paradigms of AI. NLP, natural language processing, has been here for long. It's been here for a long time, but there are ways of using it in part of speech tagging and so many other stuff we use it for. However, the coming of machine learning, like I said, is changing the game of everything. Even machine learning, AI paradigms are begging machine learning to help them to be able to go places. And that is exactly what machine learning has done to NLP. So with the combination of machine learning with NLP capacity, that's why you now have LLM. It's not, LLM is no ordinary natural language processing. It's beyond that, because it has added that learning capability. Ability to learn from text, several texts. We've been building language models. We used to teach our students build language models. What is it? When you go online, long time ago, when you are trying to Google, when you type in, Google will be suggesting the next word you want to type for you. That is language model, by the way. It's under natural language processing. It's under natural language processing. As you are typing, it's suggesting for you the next word to be typed. And it suggests based on what people are typing in your area. If you are on a campus, what you suggest for you may be different from when you are in the city or another city or another country. Because what is very common in that area that people are searching for, it will be suggesting it for you. That is natural language processing. We call it language model. Whereas I'm typing, I'm predicting for you the next thing you are going to type. But large language model has taken it now to higher level. So large language model is part and parcel of NLP. But now with large language model, we are now saying, usually when you do the modeling, large language model, we do for like just ordinary, maybe few, n is equal to 2. When we set n to be 3 or 4, your laptop may shut down after running it for many hours. It's not going to finish. But what people did was they tried to build powerful machine, put it in Siberia, very extremely cold area because of the heat this system generates. They now build language model with capacity to run for n is equal to as big number as possible. Usually my student will build a simple language model. N is equal to 1, n is equal to 2, n is equal to 3. The moment they go beyond 3, they may not be able to run it. Now people have made it possible now to run language model that is up to n as a big number. N is equal to 300 or whatever, or even more. That's why we call it large language model, LLM. It's not just the classical language model we have in NLP, it's now large language model. But when you talk of NLP as a general thing, it's still also natural language processing. What you are using LLM for is to process natural language. So it's still under NLP. So as a general big boy, LLM is under NLP. But machine learning has been integrated to NLP to make it become LLM capable. I hope that clarifies. So once you bring the machine learning capability to the NLP, we now call it LLM, large language model, and even the generative AI. I hope that clarified. Can you give an instance of parameter tuning? Yeah. When we talk of parameter, there are two types of parameter. There is a parameter that are going to affect your model. There is parameter that is just there. It's not going to affect your model. Because in computing, once we write a function, we pass some parameter to it. Like I want to, when I'm passing parameter to my code, I want it to give me answer in 2 decimal places. That 2 decimal places I've requested for is a parameter I've passed. However, 2 decimal places doesn't affect the result. It's just rounding up. But all those parameters that will affect the result of your model, we call them hyperparameter. Those are the one we tune. We tune this one. For example, k-nearest neighbor, KNN, is an algorithm. By God's grace, we are going to discuss it in the afternoon, practically how it works, and we demonstrate it for us also. In KNN, we set k to be 1. That's the default value. You build the model. It maybe it's giving you 92% or 80 something. I want to get more. I set k to be equal to 3. I take k to be equal to 5. That is called hyperparameter tuning. I'm changing the hyperparameter value to be able to see which k is going to work for me. For some application, you will get to a level before you get the one that works for you. In some, I've seen application where 1, the first one, default, work for us. We tried to search for better one. We never got anything better than 1. That is called hyperparameter tuning. We do it in every model you are building. Even when you are building the LLM family, you have to tune the hyperparameters. Those are the parameters that affect the performance of the model. It's not just cosmetic parameters like number of decimal places. No. Should I use this? Should I randomize the data or not? These are just parameters. But hyperparameters, they are parameters that affect the performance of your algorithm. If I'm building SVM, support vector machine, I'll be talking of the kernel to use. Is it polynomial? So is it Gaussian kernel or polynomial kernel or any other type of kernel? I'll be talking of C, the regularization factor. Is it 1? Is it 100? Is it 1,000? So these are called hyperparameter, parameters that will affect the actual performance of your model. So I hope that clarified, that answered the question. Yeah. Yeah, you have 2 questions. So Shen Chinyi, is that the name? Hi, I have 2 questions. Is it compulsory to conduct PCA or feature reduction during the stage of feature engineering, or is it dependent on the data characteristics? Thank you very much. Based on what I call let the data speak, people used to do in the past. Once they start modeling, they spend 60 to 70% of the time doing pre-processing. We've realized that this is not necessary. It's not every time that a data set benefits from pre-processing excessively. In fact, it may lead to what I call data mutilation unknowingly. So the best practice is study modeling. Get your data set, get it into it. Even when you have missing value, you can still use decision tree to model your data without problem. Decision tree and its family, they can model in the presence of missing value. Use them and see what you're getting. If I use decision tree on the data with missing value and I'm getting like 99% accuracy, why am I wasting my time again? It solved the problem for me. I'm good to go. But in the past, people do so many things. Normalization is good. But sometimes normalization may not benefit you. We have seen that in practice, where normalized data refuse to give the actual result we are looking for. But after we now tried the original data, we got what we have been looking for. So that's why I always tell people, don't normalize immediately. Run the experiment, record the result, go back and normalize and record the result. Compare them side by side. Which one is better? If the one normalized is better, go with normalization. If the one not normalized is better, our aim and aspiration is to get the best result. If normalization will give up, we go for it. So the same thing goes to PCA. PCA is principal component analysis. This is a means of reducing features. For example, there's feature selection. It's different from PCA. In feature selection, I have 15 features and 300 samples. Definitely, there's going to be cost of dimensionality there. So I need to reduce my feature. But before you start reduction, first of all, use the full feature. Model it and record your result. Do feature selection, reduce 15 to 3 or 4 or 5 as much as you can. Check it. Use different feature selection method. Sometimes after doing this, we didn't get the result also. Then we can start thinking of PCA, principal component analysis. I just want to convert the feature to another format. It's not getting me what I'm looking for like this. I've done many things. Nothing is working. Because PCA, we modify your features. You can say, okay, these 10 features, I want you to PCA convert it to like 3. And the 3 you are converting it to, none of them is going to be present in the original data. It's a totally different data set you're going to have when you use PCA. It's a principal component analysis. It uses a particular process to generate a different feature from what you are having. But the feature you are having is not going to be present in the one you started with. Let's say I have age as my feature, weight as another feature, and maybe another number. Let's say the two, age and weight. When you convert it to use principal component analysis to generate a new value, look at the age. You may not see the age inside it again because they have computed some things, principal component of those features. In that case, we go to all this level when we have tried basic systems we can use to get good result and we're not getting it. Okay, let us use PCA. Maybe if we try, it will transform the data into another dimension totally, and then you can use it to run your modeling, and see maybe you get better result. So during the state of feature engineering, we do this. We only do it, you should only do it if it becomes necessary. Try simple feature selection before trying going to PCA. Okay, so it depends. Once you have tried many things and it's not working, then you can go PCA, and there are so many other transformations you can subject your data. You can find the log, can log the data to base whatever you like, just to change the nature of the data. Maybe that will give you the insight you are looking for. That is when you use it. But it's not something that is compulsory that you must use. Let the data speak. When the original data set modeling is not getting good results, keep trying other methods, consult experts, and then keep guiding you until, if there's need. For me, PCA will be one of the last things I'll be thinking of for my students to use. Going feature selection can solve my problem. I don't need to go for PCA, because the implication is once you get it through PCA, anytime you get new samples to be used on this model, it has to pass through PCA also. You see? Because whatever you have subjected your training set to, you have to subject your testing set to it. That means your testing set also will take a lot of procedure before you can be getting reasonable result. So that's why if original data can get my result for me, why am I going for PCA? There's no need for it if you can get it without that. Hope that clarifies. I usually use portion of 70-30 for the training and testing, but sometimes I will be having low producer accuracy. How can I improve my data feature? Well, there are several things you can do. Like I said, one of the simple things you can do is do your hyperparameter optimization. That's the first thing. That's the first thing you have to do. Hyperparameter optimization. Once you run a model, 70%, 30%, or 80-20, and you are not getting good results, 30% should not be used in hyperparameter optimization. A lot of people are doing this. It's a big mistake and a wrong way to run a model. Because when you use 70% for training, 30% for testing, so the result is bad, I will use case go to 3. You are using your testing set to modify your hyperparameter. That is not correct. You're already exposing the testing set to the data. You're supposed to keep 30% out, use cross-validation of 70% that is inside for your hyperparameter optimization, and later build the final model using the 70% training and bring in 30% for the final checking. All this we are going to demonstrate today, by grace of God, in the afternoon. So this is what we should take note. So if you are not getting good results, you can improve it. Try normalization, normalize your data, but keep the original data first. It's not working, maybe you do feature selection. How many features is good? Exhaustive feature selection is the best, where you can try different combination. Use 1, use 2, use 3, A, B, C, B, C, D. Different combination, but if your number of features are many, you cannot use exhaustive feature selection because it's going to be combinatorial explosion. You cannot finish. It's an NP complete problem. In that case, you have to use like recursive feature elimination for the feature selection. Use all the features, divide into 2, rank it according to correlation coefficient. The features, how are they correlated to the target? Rank it. Divide into, use all of them, divide into 2, use the best highly correlated top features, best half, divide that half into 2 again, use the best half again, keep dividing into 2 until you have only 1 left. By so doing, you may be lucky to get the best features that will work for you. And there are so many other things we can check. In the worst case scenario, you may go for your ensemble. Try to build model from different algorithms. You know, I told you algorithms, different algorithms are using different feature space. So if all of them look at your data from different angles and you combine their judgment together, you may be able to get better results. Yeah. Sorry, you should be able to unmute yourself, I believe. Sorry, yeah, you can unmute yourself. Sorry. I hope I answer your question. You can unmute yourself now. Hope I answer your question. The question is, if machine learning is fundamental about extracting patterns from historical data, how do we build systems that can create genuinely novel solutions rather than merely extrapolating from the past? Is there a theoretical limit to innovation in data-driven intelligence? Yeah, it depends on the problem you want to solve. Okay? There's so many areas you can actually innovate and use AI, machine learning, to assist you. However, know that this is introduction to machine learning. Okay? We will not start from the top of machine learning. We start from the simple one that people can relate with easily. So there's no limit to the level of innovation that you can use machine learning for. There's no theoretical limit to it. Whatever you want to do, bring it up and then discuss with people of expert in that field and see how much you can actually have. A lot of reverse engineering stuff have used machine learning to facilitate how they can actually do it and make it actually better than what ordinarily was initially possible. So there's no limit to the imagination and what you can use machine learning for. But that's why, you know, we have different type of AI. We talk about, if you remember, if you didn't miss that, we talk of supervised learning, unsupervised learning, reinforcement learning, LLM, deep learning. So there are so many types of machine learning. So it depends on which area you're applying it and you want to apply it. So in short, to answer your question, there's no limit. So the new and the theoretical innovation that you can bring data-driven intelligence to. Depend on your innovation and how far you can go. Now, okay, I believe there's questions on board. Now, there are 2 people raising up hand. We call them stars. I have Mr. Kabiru Saka. Mr. Kabiru Saka, you have the floor. Can raise up. You can unmute yourself and ask your question. Is the hand still there? We can't hear you. You can unmute yourself. Not unmuting? Can you try it now? I allow you to unmute. Can you try it now again, please? Still not able to unmute yourself? Can you try it again, please? It should allow you now.
Thank you, Salam. So, thank you, Prof, and good day to everybody on the calls. My question is a very straightforward one. During your explanation, you made us realize that there is a need to segregate data into the training and the test sets. But I think that the results you are going to get sometimes will depend on how that segregation is done. So, for example, if your data is sorted, probably by one of the features, and you just select the top data for, say, your data sets, and then the remaining for your training sets, you're likely going to get a worse performance compared to if your data is not, is not sorted. So how do you prevent this kind of things happening? What strategies is done to avoid this when doing data segregation into training and tests? Thank you, sir.
Okay, thank you very much. Thank you very much for bringing that up. Well, yes, when you bring your data set, usually there are systems built to help you. One of the things they use in data partition is randomization. It's always good. If the data is sorted, it's dangerous. So yeah, like you said, so you'll be taking a particular category of the samples for training. So the other sample will be totally different from what you train on. That is definitely inviting chaos, not being able to have good generalization. So that's why one of the principles in the partition the data is to randomize it. To randomize it, make sure that data that are closely related are not the ones that are always together. Another thing we also monitor is we call something stratify. It's not just randomization. Stratify, sampling approach. When you say you want to use stratify approach, it takes care of the randomization and the like. Stratify. Stratification. See, when you are trying to partition the data, this stratification is very important. Let's say we have 1,000 samples. 1,000 samples. You just break the data, you broke the data into two, 70% for training, 30% for training. Meanwhile, in this 1,000, there are 600 cases that are maybe class A, and 400 class B. If you divide the data, 700 is going to be the training set. You may have a situation whereby all the class A, 600, plus only 100 from 400 to make 700 are partitioned into 70%. All the testing set belongs to one class B, 300. That would be a problem. If we don't testing set, one class is not being represented. So this is why when we are partitioning our data, we stress this idea, stratify sampling approach. That stratification will ensure that when you are partitioning your data, the 400 that belongs to class B, 70% of it must go to training and 70% of it must go to testing. The same thing go to the 600 of class A. You have to ensure it, especially when we do cross-validation. Remember cross-validation? I said you are going to partition your data into like 5 places or 10. This is having 100, 100, 100. You have to make sure that the 100 in this sample does not contain only one class. Otherwise, there's going to be a problem. So that is why when we are partitioning, we don't sort the data. That will lead to trouble. And also, not only that, we have to focus on the target also. All the class A must not only belongs to one partitioning, while all class B belongs to. If we take it, the first on top, we may likely maybe the last below, they are the one that are belonging to different classes. Because when you are collecting data, people start collecting data from people who are sick, diabetes patient. After they are done, they went to add patients that are not sick in order like that. So if you just take the 470, 700, and then the next 100 and next 10, 300, we may be partitioning into trouble. So thank you very much for that question. And now we've clarified, we have to use stratified approach. Most of the partitioning system take care of that. Like Weka, now when you partition into Weka, stratification is built into it automatically to make sure that every partition has fair representation of the classes that you have. And also make sure that you randomize your data before the partition. That's a very good question. Thank you very much. I believe those are the questions we have for the day. So, is there any other question? Otherwise, coordinator, over to you.
Thanks so much once again, Prof. I'm just looking at I wouldn't know if it was the last speaker or the questioner, Mr. Jamal, saying I'm not able to unmute myself. Was he the last questioner?
Okay, Mr. Jamal, he didn't raise up his hand. If you want to ask question, you can still ask. Though we have already passed out.
But I could say I'm not able to unmute myself.
That was
Mr.
before.
Jamal, are you there? But if you cannot unmute yourself, you can put your question in the question chat.
Maybe it's on inside. It's there. That's Dr. Jamal. Maybe it's not there. So he can catch up in the next class, no problem. That's fine.
Okay. So thanks so much, Prof. Once again, we really enjoyed both the sections and the question and answer section also. Thanks so much for the effort.
Before we go, let me answer. There's one person say, Mikdad Bada. Say we have not answered your question. Please, what's your question? Can you unmute yourself and answer your question? We read the questions and answer them. Can you answer? Are you raise your question? Mr. Mikdad Bada said the question is not yet answered. Maybe it's not in there. So later I can bring it in. It's okay. I believe we can bring this session to an end. So people to move on their break and come back for the next section. Thank you very much.
Thanks so much, Prof. On the final note, please, we are to come back for the second leg of today's session by 2:30. Please let us be prompt and so that you can start the question by exactly 2:30 because it's going to be 1 hour 30 minutes, 2:30 to 4 o'clock. And for those of us, like someone like Migdad, and if your questions or your concern is not answered, you can pen it down. When we come back, you can also ask, despite that the lecture wasn't in the same session, there's no problem. It's going to be taken and it will be answered. Thanks so much for the attendance, and I believe everybody has registered, has filled the attendance register. I read on the platform that someone was saying it's not going. Even myself, I filled it. I am not too sure if we had such a problem, but it's still there now. If you have not filled, please kindly fill the way you want your name to appear on your certificate. I see you in the next session for today's class. Bye.
Bàbá fún prógámù náà lẹ́kùn.